Welcome back, everyone. Today we'll be covering Chapter 16, System Evacuation, Leak Detection, and Recharging. Our objectives are to evaluate the reason for performing a proper evacuation, recognize the factors involved in a time-efficient evacuation, describe and demonstrate the two main methods of evacuation, identify and correct contamination problems, identify and describe the different types of refrigerant leak detection, determine the proper system pressure needed to check for leaks, detect refrigerant leaks using approved methods, use refrigerant cylinders properly, predict and correct low side pressures, recognize and eliminate causes of high head pressure, use electronic scales and graduated cylinders for charging. System evacuation. To operate at its peak efficiency, refrigerant needs to be pure, clean, and dry, accomplished by installing all system components tightly, locating and repairing any system leaks, performing a proper evacuation on the system to remove any moisture, air, or contaminants. Moisture. Moisture in a system can cause damage. In low temperature, water will freeze and cause a blockage. Remove as much moisture as possible, evacuation and use of dryers. A vacuum pump creates a very low pressure and removes moisture and contaminants. Evacuation should be performed whenever a system has been contaminated or exposed for a prolonged period of time to atmospheric air. Evacuation factors. Before evacuation, a system's pressures must be reduced to atmospheric 0 psig. Proper evacuation using a two-stage vacuum pump to pull down to 500 microns. A proper vacuum is one of the most important steps to having a clean and dry system. Time required for evacuation. The time required for a vacuum pump to remove moisture and air from a system depends on several factors. Size of a system, amount of moisture present in the system, capacity of vacuum pump, size and length of connecting lines, condition of the vacuum pump oil. Using heat during evacuation. Heat can help release trapped moisture. Use gentle heat sources such as a heat lamp, never a torch or steam. Recommended vacuum pump sizes. Suggested minimum vacuum pump ratings for systems of different sizes. Up to 7 tons, 1.2 CFM. Up to 21 tons, 3.0 CFM. Up to 35 tons, 5.0 CFM. Up to 70 tons, 10.0 CFM. Up to 105 tons, 15.0 CFM. Size and length of connecting hoses is also an important factor. Micron gauge. A highly accurate vacuum gauge. The only way to know when 500 microns has been reached is with a micron gauge. With the new digital gauges, it will have a built-in micron gauge. So you wouldn't have to worry about buying an extra gauge. Deep vacuum evacuation. Pulling the system down to a vacuum of 500 microns in one long pull. Takes time to pull out air and moisture that might be trapped in different areas inside the system. After reaching 500 microns, isolate the system from the vacuum pump. Watch the micron gauge for a while. If the reading stays at 500 microns for 15 minutes, all moisture has been removed. Triple evacuation. Pulling three separate vacuums and injecting nitrogen into the system after the first and second vacuums. Nitrogen will help dry out the system, allowing the vacuum pump to perform better. If a 500 micron vacuum does not hold after the third vacuum, there may be a leak in the system. Harmful contaminants may be brazing flux, metal chips, wax, acid, oil, sludge, dirt, black oxide, and rust. Sludge traced to the high compressor discharge temperature and presence of contaminant. Air in the system causes high discharge pressure and high temperature. Oxygen and moisture can cause breakdown of oil refrigerant mixture to form acid. Oxygen also causes rust formation. Contamination during brazing. Brazing can cause black oxides to form. No harm if formed on the outside of the tubing. If formed inside, they can circulate through the system. Avoid this by sweeping with the following of low pressure inert gas, 2 psig to 3 psig. Pressurizing regulating valve must be used with the inert gas for safety. So this is done using a valve to allow a small bit of nitrogen to flow through the system while you're brazing. Using an inert gas for brazing. And here is a chart showing you. Leak detection. Leak detection should be secondary to leak prevention. Leaks may be caused by vibration, poor brazing techniques, improper use of fluxes and brazing materials, and poor workmanship. Various leak detection methods and procedures are used. Vacuum method. System is evacuated to a deep vacuum, isolated from the vacuum pump and monitored using the gauge manifold. If the vacuum remains, most likely leak-proof. Only reliable for detecting major leaks, requires considerable time and energy. The bubble, the bubble method. And guys, this is the method I use always. It's just the easiest, the oldest. You just need bubbles and you'll see your leak. Oldest and least expensive method available requires system to be pressurized equal to the low side test pressure listed on the nameplate. Slope solution must be a proper consistency. Apply solution generously to test area. Allow time for small leaks to appear. Test in most likely spots first: joints, fittings, service valves, and condensing unit. Pressurizing the system. Nitrogen or carbon dioxide used to pressurize system for leak detection. Never turn a system on with inherent gas in it. Pressure regulator should always be used. Deterrent solution. Available at refrigerant supply houses, applied with dabber or as a spray, check system, and also gauge manifold and hoses. Halide torch. Fast, reliable method for detecting halogen refrigerant leaks. Detects very small leaks. Hold sniffer hose around the suspected leak areas. Flame changes color to no longer is widespread use. Electronic leak detectors. This is another method that I use. So I usually use the bubble method and electronic leak detector. Extremely sensitive and easy to use visual indicator and or audible signals used on system with refrigerant in it and up to low side test pressure. Can be recalibrated, confirm leaks by applying bubble solution. Ultrasonic leak detector. Here's the hiss of a leak. Responds with audible or visual indications, pinpoint leak regardless of contamination, and works on pressurized systems or a vacuum. Highly directional, useful in confined spaces, troublesome in wide open windy areas. Sound level can be artificially increased by spraying leak area with plain water. Oil as a leak indicator. Certain amount of oil escapes at the site of a leak of a refrigerant leak. Fresh oil indicates the system has a leak. Oil spills should always be cleaned up as a safety measure. Cleaning up oil also makes it easier to spot new oil spills. Dyes. For injecting into the compressor crankcase oil at a leak, oil and dye escape along with the refrigerant. Glows fluorescent in presence of ultraviolet light, effective in locating low-level leaks. Allow adequate time for dye to circulate before checking for leaks. Standing pressure test. Determines whether all leaks were found. Recover system's refrigerant charge. Raise system pressure to low side test pressure using inherent gas. Measure and record system pressure and ambient temperature, then isolate the system. After several hours, check and record new pressure reading and ambient temperatures. Consistent pressure, according to ambient, means that the system has no leaks. Refrigerant cylinders, either steel or aluminum, available in a number of standard sizes. Most have pressure relief device required by the US DOT on cylinders more than 12 inches tall and 4.5 inches in diameter. Must be inspected every 5 or 10 years, depending on type of refrigerant. Steel cylinders. Dual valve withdrawal refrigerant as vapor or liquid should never be completely filled with liquid. Allow space for hydrostatic expansion. Full when 80% of interior space is occupied with liquid. Disposable cylinders. Throwaway cylinders available in sizes ranging from 24 to 50 pounds. Handles on top protect against damage to cylinder valve. To withdraw refrigerant vapor, use a cylinder in upright position. To withdraw liquid, invert the cylinder, or if equipped it with a dip tube and dual valve, use a liquid valve. And here is a picture of disposable cylinders. And these will be the cylinders you'll be buying, like when you buy refrigerant, new refrigerant to put into a system. Recovery cylinders. Refillable heavy-duty certified pressure vessels meeting DOT specifications, gray bottoms with yellow tops, must be inspected at regular intervals, repaired or replaced when damaged. Recovery cylinder. Proper procedures must be followed when using cylinders. Amount of refrigerant measured in pounds. Leave 20% space for hydrostatic expansion. Clearly label according to its refrigerant. cylinder safety. Label with a DOT classification tag. Secure firmly when storing or moving. Never mix different refrigerants. Do not vent to the atmosphere. Do not use damaged cylinders. Restore in vertical position with valve at the top. Retest and recertify every 5 years. Pull in a 20-inch mercury vacuum before filling. Never fill more than 80% of volume. If exposed to temperatures above 130 degrees Fahrenheit, do not fill more than 60% of volume. Weigh cylinders on accurate scale. Never use disposable containers for recovery. Before discarding, recover any refrigerant inside. And here you have a PT chart. Controlling low side pressures. An evaporator provides cooling by producing low temperature from evaporating a liquid at low pressure. Low side pressure reveals a refrigerant saturation temperature. This corresponding value does not include superheat. When the system is not operating, the temperatures of refrigerant, evaporator, and return air are the same. No temperature difference. No TD exists. Low pressure produces temperature difference, which produces cooling. Rule of 10. Evaporator refrigerant is 10 degrees colder than evaporator tubing. Tubing is 10 degrees colder than return air. Temperature difference. Necessary for cooling and obtained only when the system is running. To maintain air temperature, a thermostat may be located within the airspace. When air temperature reaches highest set point, system switches on. When an air temperature drops to lowest set point, system turns off. Many systems are turned on and off by pressure control. Evaporator airflow. To maintain proper TD, temperature difference, the amount of airflow across the evaporator must be correct. Medium temperature 1,350 CFM per ton, low temperature 2,000 CFM per ton. Too large of airflow results in very cold evaporator with low refrigerant pressure as the heat load cannot reach evaporator in sufficient volume. Excessive airflow results in high temperatures and pressures. Air conditioner temperature difference. Airflow of 400 CFM per ton. Evaporator should produce a temperature difference of 15 degrees to 20 degrees Fahrenheit between return air and supply air. Total temperature difference calculated from supply air. Controlling high side pressures. Condensing unit is designed to convert refrigerant vapor into a liquid for reuse. As ambient air temperature goes up or down, high side pressure temperature also goes up or down to maintain a temperature difference. Balance point must be maintained. Air-cooled condensers. Balance point of the condenser, high side pressure, can be predicted. Compressor must compress gas to a saturation temperature of 30 degrees to 35 degrees Fahrenheit above ambient air temperature. Use pressure temperature chart to determine proper head pressure. And that was that rule that I would always talk about in class, 30 degrees above ambient. That's why I kept on repeating it. I told you we would get to it. Water-cooled condensers. More efficient than air-cooled condensers. Head pressure should correspond to condenser water out temperature. Excessive head pressure. should be avoided as it reduces system efficiency and causes compressor problems. Five possible causes: air in the system, overcharge of refrigerant, dirty condenser, reduced air or water movement, high suction pressure. Charging refrigerant into a system. Charging means to add refrigerant. Systems use different kinds and amounts of refrigerant. In some systems, amounts are critical. Refrigerant can be charged into a system as a vapor or a liquid. Before charging, a system must be tested for leaks and thoroughly evacuated. Vapor charging. Charging refrigerant vapor into the low side of a system using a low side service valve. Cylinder pressure must be higher than suction pressure. Avoid charging too quickly, raising discharge pressure. Liquid charging. Charging refrigerant liquid into a refrigeration system faster than vapor charging requires skill and experience. Meter the refrigerant into the low pressure side. When liquid charging, you would want to do it when the system is off, but then it will equalize. So after that, you turn on the system and then you vapor charge. You could liquid charge, but you run the risk of slugging your compressor. If it's a, a package unit or a unit that has an official weight stamped on its nameplate of charge, what I like to do is just pump in the charge using the recovery machine. I will be posting a video later on of me actually charging a system, and we'll go through these procedures. Charging by weight. Small self-contained systems are usually charged by weight of refrigerant. Recommended charge stamped on data plate. Two common charging instruments: electronic scale or graduated cylinder. Electronic scales, accurate, easy to use weighing devices. Remember to zero out the cylinder or other setup controls before charging. Different models and controls available. And this is what you'll be using. Um, the next slide is the graduated cylinder. Um, but to be honest, this is not used that often anymore. You'll be using the electronic scale. But the graduated cylinder measures the refrigerant by volume rather than weight, allows for precise charging. And this is the last slide. Like I said, I will be posting a video probably later this week on me doing a repair, checking for leaks, and charging the system. Thanks for tuning in.